There it is.
Okay, well, without further ado, let's get started. So today is, let's say, the first real lecture of Riemannian geometry. What we've been doing up to now has been sort of fits in the framework of differential geometry, but it doesn't really have much to do with the things you think about when you think about Riemannian geometry, which is curvature and length and all that. Well, curvature, I guess. So today is our first lecture on curvature. Okay, so the outline for today, since I guess Justin did this a little bit in his lecture, but it's because we've got out of sync a bit. I just want to state for the record how you find normal vectors. And then I'll talk a bit about surface integrals and surface area because we'll need that for later. And then we start to get into curvature. So the starting point for curvature is going to be the Gauss map. And you've seen the terminology Gauss map before in the context of curves. In this case, it's something a bit different. In any case, it'll lead us, related, in any case, it'll lead us to the second fundamental form, which is the this idea of extrinsic curvature of a surface. There's such thing as intrinsic, we'll talk about that later. But anyway, the Gauss map leads directly to the second fundamental form, and then we'll spend the last bit of the lecture just interpreting the second fundamental form in a bunch of different ways. Okay? So just to make it complete and clear, how do you find the unit normal vector of a surface? Well, the first question is the unit normal vector of a surface a geometric object to begin with? So remember what geometric means. It means somehow, canonically defined, independent of coordinates and all these things. So is this a geometric object? Well, so the answer is a little bit subtle. So it turns out the normal line, the direction normal to a surface. So if here's your favorite surface, then this is the line which passes through the surface perpendicular to the surface. The normal line is geometric. Justin, could you turn on one, or maybe open one set of blinds to shed a little light on the blackboard?
Mm-hmm.
Yeah, that's probably good. Everyone can still see this, right? Okay, cool. Okay, so the normal line is a geometric thing. Why is it geometric? Because the tangent plane is a geometric object. And once you have a tangent plane, there's one and only one unique normal direction to a tangent plane. This is why the tangent line is a geometric object. But more than that, you can't really say. In fact, you can't even say which direction is up, which direction is down. That isn't a geometric thing. And then choosing a unit normal vector, using a unit normal vector is related to choosing a direction, right? Because length is well defined, so you can always make something unit length. But getting it to point consistently in one direction or another, that is a choice you have to make. That's the non-geometric part. The thing about non-orientable surfaces, which is bullet up there, is that it turns out you can't always define a unique normal direction, a canonical normal direction consistently. And the favorite example of this is the Möbius strip. So how good am I at drawing Möbius strips? This, I think. Does this look vaguely Möbius strip-like? There's something missing, I think. How does it go? Yes. Is that a Möbius strip? Maybe? Let me write it down so you can look it up. But you guys know what this thing is, right? It's to take a piece of paper, put one twist in it, glue it back together again. So this has the property that if you decide, that if you're standing at this part of the surface, and you decide, okay, this is going to be my forward direction on the surface, and you walk all the way around the surface, by the time you come back to where you started, you're pointing opposite to your initial decision. So this is this phenomenon on a non-orientable surface like the Möbius strip. You can't assign a unique normal direction. So there's this choice, either if you're orientable or if you're not. And if you're not orientable, so there's this dichotomy, orientable or not. And if you're not orientable, then you can't go further. If you're orientable, however, then you can make a choice. At one place you decide that's forward, and then you can extend that decision continuously over the entire surface. Okay, so this is how you get your hands at a normal direction and a unit normal vector. Okay, what about concretely? And by this I mean locally. Well, locally you can always do this. The connection between this point here and the point above it is that this local decision doesn't always extend globally. But in any case, if you're in a small neighborhood of the surface and you've made, you're sort of in this neighborhood over here, in the image of a parameterization. There's some parameterization. Then you can always get your hands on some vectors, E1 and E2. You can always get your hands on some tangent vectors. If you have a local parameterization of the surface, you can get your hands on some tangent vectors. And then once you have the tangent vectors, maybe I should change this one a bit. Once you have the tangent vectors, then the unit normal vector field is just the cross product of the tangent vectors divided by their length. So locally, you can always construct a normal vector. It's just you can't necessarily extend it all over the entire surface. Anyway, this is how you do it. Okay, so one last point on normal vectors is that in the case of a level set representation of a surface, you actually have a really nice formula for the normal vector. So maybe I'll work this out over here. I'll walk through this over there. So, so just a reminder, f inverse of some value v, if f is a function from R3 into R, then f inverse of v is the level set for value v. This is the set of points x in R3, so that f of x is equal to v. So it's the level set of value v, all the points whose function value is equal to v. So I don't know, here's a sort of a schematic picture of the level sets of the function f. I'm drawing this in R2. So this is f of x equals to v. This is f of x equal to v prime for some other v prime. And then furthermore, etc. So, the level sets, the values of v foliate the space. Okay, so so this is our picture. And now let's take a curve that lives inside one of the level sets. A curve C, I don't know, some interval into R3, such that C is contained inside the level set, f inverse of v. And of course, what that means is that C of t belongs to the level set for all t. And what this means, every C of t lies on this blue curve where the value of f is always equal to v. So in other words, f of C of t equals to v for all t. So this is what it means, or this is a consequence of the curve lying in the level set. Okay? Does that make sense? Okay, so now we're here, and well, we have this right-hand side depends on t, left-hand side is constant. So if I differentiate, I get zero derivative on the left, and my nice formula is going to show up on the right. Okay, so what I get is 0 is equal to d by dt of f of c of t. And let me go ahead and take t equals to 0, and let me just say that here is the point c at 0, which is just some point p, which sits inside the level set v. Okay, so if I do this derivative, then what I get is, by the chain rule, I get df by dxi at p multiplied by dci by dt summed over all I. And this is at 0. Or I get the derivative matrix df at p transpose inner product here, with dc by dt at 0. So that's my relationship right here. Except for one thing, which is I denoted this vector here by x. So let's just rewrite this as it is written on the board. df at p transpose comma x is always equal to 0. And of course, this now holds true for all curves, which means for all possible choices of tangent vector in the tangent space of the level set at 0, at v. It holds true for all curves in the level set. So therefore it holds true for all those tangent vectors of curves which are tangent to the level set. Okay, so this is our derivation. Uses the chain rule as always at the crucial place. And we can then conclude that this vector, this df, this derivative matrix, derivative vector transpose, is orthogonal to all x's in the tangent space of the level set. In other words, it's just orthogonal to the tangent space of the level set. Okay. So that means this guy here is the normal vector, or is a normal vector. Perhaps the wrong length, it's not unit, but that guy's normal to the tangent space. So since the picture over there is getting a bit cluttered, let me just redraw the picture so you have it now. Here are the level sets of the function f. And here's my point p. Here's my vector x that I did my calculation with. And here is my vector df at p transpose. And it is normal by the calculation. Okay? So unit normal is easy, just divide by its length. And remember that in order to divide something, in order to divide this by its length, this has to be non-zero. But I'm going to go ahead and assume that my surface, my level sets, are a level set of a regular value, which means that derivative is non-zero, so I can go ahead and divide by it, and it's okay. All right? And you know that if you've read the supplement, then you know that regular values are important, because, in fact, if v isn't a regular value of f, then the surface might not be smooth at that point. Right? So you do need to consider regular values in order for this calculation to go through. Okay, so there's your construction of the normal vector. The gradient of f in this derivative matrix of f is the normal direction, gives you the normal direction. Okay? Okay, so far so good? All right, moving right along. Okay, so the next topic is the idea of finding surface areas, and maybe the title of this slide should have been surface integrals. So what you usually have is you have some surface, and then you have a real valued function on the surface. And what you want to construct, you want to construct some notion of f d. Well, you want to construct some notion of the integral of a function over the surface. And in Riemannian geometry, in fact, with what we've done so far, you can come up with the right quantity, the right way of defining this object. So what we're going to do now is just walk through this slide, which is the definition of this integral. Okay, so here's the first idea. Is, okay, you have your surface here, and then you have a parameterization. which maps to some neighborhood, right? It maps in here. Okay. So the first idea is to take a parameterization of the surface and try to work inside the parameterization. So let's call this parameter domain U, and let's call this just phi of U. Right? Okay, so somehow the first idea, which is to say, oh, I should say one more thing. Once you've done this, right, so you have the function over here, right? You have the function f over here. There is an associated function on this side. Right? F gives rise to a function down on the parameter domain. What would be the form of that function? I map from up here into the reals. How can I map from down here into the reals? Yeah, right. So over here, you map surface into reals, and down here, you do this. It takes you from U into the reals. Right? Because you start with a point in U, phi takes it forward to somewhere inside on the surface, and then f takes it forward then to the reals. So f compose phi goes all the way. Right? Okay. So the first idea is to say, what we want is this. So du1, du2. That's the first idea. That's the first idea, right? It kind of makes sense. You have this function upstairs. It's defined in some abstract way on the surface. I want to make it real. How do I make it real? Well, I look at it through the lens of the parameter domain. So I compose it with a parameter domain. Now I got this function taking you from R2 into R. That's a thing I can get my hands on. Math 52 says I can integrate that thing. So here's a real value function, and I'm going to integrate it du1, du2 over the parameter domain. Okay? All right. But what's the problem? Because there's a problem with this first idea. It's not a good idea. What's the problem with this first idea? Say again? Okay, so let's say that's the hint to the solution of the problem. So good job. Well, what's the problem? What's the first problem that we have to solve here? Yeah.
Uniquely defined.
Okay, uniquely defined. Why might it not be uniquely defined? Because you can have lots of charts. You can have lots of parameterizations. There's lots of different choices of u and phi which cover the same surface. And so, well, it's this point down here. Is this definition independent of the parameters? Is it well defined and unique and independent of the parameters and makes sense as a geometric object? And the answer is already up there. It's no. So this depends on the parameterization. Okay, so we're going to go over there, and let's just solve this problem. And the solution is Mike's solution, in fact. Okay, so, right. So what we have to do is walk through these three sub-points up there and see what's going wrong. So let's draw the picture again. So here's the surface, here's the coordinate chart. So u, and then phi maps it forward, and you end up over here somewhere. Okay, so the issue is that phi takes small rectangles and deforms them. Remember the mapping of a small rectangle. Well, mapped by never mind where. Small rectangles are mapped forward on under the linear transformation d phi, and they don't end up as small rectangles over on the right-hand side. They end up deformed, right? So you end up with some sort of lozenge type shape over here, right? A deformed rectangle. This is d phi of, let's call it r for small rectangle. This is r. Okay, so a square rectangle gets mapped to a deformed rectangle, or a deformed parallel pipeline, a lozenge. And so, yeah, so this is the reason why this integral doesn't make any sense. Because over here, you're kind of saying, let's pull the function back, and let's integrate it against small little, let's sum up its values over small little rectangles. But that doesn't quite work with the surface, because a small rectangle on the right is not a small rectangle on the left, and vice versa. Okay? So somehow you have to build in a factor which compensates for this angular, this flattening effect. Okay, so this is the problem. So the problem is that rectangles are badly deformed. Not badly deformed, but rectangles are deformed. Okay, so there's the problem. And, well, the solution is you want to compensate for this. Okay, so the key, actually, is to write out the Riemann sum. You know, every integral equals the limit of a Riemann sum. The key is to write out the Riemann sum correctly. So, the Riemann sum should be the integral of f over the chart is approximately equal to, and in fact equals to the limit, so let's say approximately equal to the sum of f composed phi at some point ui multiplied by the area of the small rectangle at ui. And you want to sum this over all the i's, and then, you know, there's these rectangles. Yeah, okay, so let me just draw the picture, I guess. I should add a picture to this. So here's my surface, as usual. And over here in the coordinate chart, what I've done is I've broken the coordinate chart up into lots of small little rectangles. And let's say this guy here is the rectangle centered at ui, and it gets mapped over to some lozenge over here, which is a lozenge centered at phi of ui. So the ui's are just a whole bunch of points. So ui equals points in u, sort of a network of points spread out evenly, maybe on the corners or in the centers of all these rectangles. That's where the ui's are all located, right? The ui's are all here. So what you want to do is add up a bunch of f-composed phi's centered at the right places. But you want to multiply by this compensating geometric factor. The logic being, this whole thing is supposed to live on the surface S. So, in other words, the correct weight to put behind this thing is the area of the associated deformed rectangle. Okay? Right, so let's look over here. Right, so if you have two vectors, E1 and E2, and if I put a little wedge between them, what that wedge means is it's not about a coordinate rectangle, right? The wedge of two vectors is a coordinate rectangle. So the area of a coordinate rectangle spanned by two vectors is the length of their cross product, elementary geometry. Does everyone remember this fact? The length of the cross product is the area of this lozenge, right? So the length of the cross product, if you work it out in terms of d phi, in terms of the derivatives of d phi, what you find is you get the determinant of this matrix right here, this d phi transpose d phi. So the area of a small rectangle is this determinant factor. Okay, if I stick that together with this, put that together with the Riemann sum, I get this expression right here. So this Riemann sum is the correct, properly compensated integral. Riemann sum is just going to converge the integral. And then you take the limit, some analytical details aside, with convergence and so on. In any case, you take the limit as the number of rectangles goes to infinity, and then you get this quantity, which we're going to call integral of f dA, or d area, just to indicate that it's geometric and lives on the surface. And the compensating factor is this so-called Riemannian area form. It's not du1, du2. It's this determinant, square root determinant factor multiplied by du1, du2. Okay, and the last thing to say about this is we know we've done the right thing because at this point you can now work out a change of parameterization. You can change the parameters. And what you would want to check is that the form of the integral is the same. I mean, not the form of the integral. The integral itself is the same before and after you change parameters. So we've done one type of change of parameters calculation in full detail. We did a second one, we sketched it out a little bit. Can someone sketch out how this might work here? How you might get the change of parameterization formula here? Someone have any ideas? Okay, so here's a hint. When you change parameters, u becomes, I don't know, g of v, where g is some change of parameters function. U changes to v. So that means you've got to make two changes in this integral. The first is these u's have to become v's, and the second is these u's have to become v's. So what happens when you change coordinates in an integral? What kind of stuff happens? Anyone remember? Determinants? Do determinants show up? Okay, so you should look back at your Math 52 notes, because if you do remember that if you do an area integral over du1, du2, and you change the u's to v's, you get a quantity times dv1, dv2, and that quantity is the determinant of the change of coordinates map. You guys remember this vaguely? Does it ring any bells? Okay, so if I change coordinates here, I get a determinant. Guess what's going to happen when I change coordinates here? You're going to get 1 over a determinant coming out. So it's a little bit of effort to prove that that actually happens. It's a bit of an involved calculation. And I promised before, we won't do this every single time, so we're not going to do it here either. But in any case, just if you're curious, or if you want to ask me, or if you just want to know the general details, or the gist of it, you get a determinant factor coming out here, and then you get the opposite determinant factor coming out there, and the two cancel, and therefore this Riemannian area form remains invariant under that coordinate change. That's why this whole thing is the right thing to do. Okay? All right, that's the end of this slide. So any questions on this? Okay, so moving forward to the next. Now I can tell you, or remind you, I guess, because it is quite similar, at least at this stage, to the Gauss map from before. Let me erase for this. You guys can take a short second break. Okay. Any questions on the previous stuff? All right. So what's the Gauss map? Okay, so the Gauss map, we've already looked at this. It's in the context of curves. The definition is the same in the context of surfaces. So what you have is your surface here, and at every point you can have a unit normal vector, and then we say we are going to be on an orientable surface, so that this makes sense. Right? There's the unit normal vector. And what you do is you move it to the sphere. So every unit vector is the vector of length 1. Therefore, if you take its base and you stick it at the origin without changing the direction of the vector, the tip is going to be on the unit sphere, right? So we have our unit sphere over here. And let's see if I get a vector which looks maybe parallel. This is n of p, which is, by definition, np moved to the origin. Okay, so that's very simply the definition of the unit sphere. The Gaussian. Okay, so this is the same thing we did before, and except on a curve. And on a curve, we talked about the turning angles, and we had very sort of topological results that came from having this formulation. We're going to eventually do something similar, but not for a little while. In fact, what we're going to do first, well, we have this, if you want a differentiable surface, the Gauss map is differentiable. What we're going to do first is study the derivative mapping, the differential. Okay, so because the Gauss map goes from S, so we have n going from S into the unit sphere, then the differential at some point P goes from the tangent space at S into the tangent space at n of P, at np of the unit sphere. So so we're going to study this differential. And it turns out some interesting geometry comes out of the differential. Okay, what does the differential do? Remember what the differential does. It operates in the tangent space. So it's a linear transformation of this tangent space here. This is Tp at S. And inside that tangent space is, let's just take some vector, say x. X is some tangent vector to the surface. And what you get on this side well, you get an image point. At the image point of n, you have another tangent space. So this is the tangent space at np of the unit sphere. And that x maps over to a vector on this side. So this is dn at p of x. So the differential, the Gauss map, takes vectors to vectors in the tangent space. That's the tangent space of the unit sphere. Okay, so this last point, somehow it's important from a technical point of view to get everything right. But in fact, I want to view this dn a little bit differently. What I would like to say is this thing here is actually has a slightly different formulation. We'll actually think of it as a mapping from the tangent space back to itself. This isn't strictly allowed. But we're going to do it anyway. The reason we can do it is because both the surface and the unit sphere are embedded in this. You can view them as being embedded in the same ambient space, the same background space R3. If S were a surface that was sort of an abstract two-dimensional manifold, you wouldn't be able to do this, but that's okay. There's a different way of dealing with the second fundamental form in that case. But for us, what I'd like to view is I'd like to sort of cheat a little bit, and I want to view this dn, this differential, as being a map from the tangent space to itself. Why am I allowed to do that? Well, because the sphere at this point and the surface at this point, actually that's the same tangent plane. I mean, there are different spaces. Like the surface may be way the heck over here, so you have a tangent plane over there, and the unit sphere may be centered at the origin. but it's the same, it's a parallel tangent plane. It's the same one. And the reason it's the same one is simply because they have the same normal vector. Right? The normal vector at that point is NP. The normal vector at this point is NP. So I got two parallel planes. So I'm allowed, if I want, just because background space is Euclidean, I'm allowed to take this plane and slide it over and identify, or I mean, I guess this one, and identify the two. Right. So I'm allowed to say, in this case, that dn maps TP into TP. So this is my Gauss map, and it's going to have this form, and well, I'm sorry, this is my Gauss map, and this is my differential. It's going to have this form, and we're going to study the differential of the Gauss map. Okay? Sorry, it's a little bit of a long construction here, but maybe I guess I could have short-circuited this a little bit. But in any case, this is a standard construction which brings us to this differential. Okay, so now we, I guess, I'm sorry.
So you're saying because the tangent planes are parallel, you can like identify them.
Yeah.
Does that mean because you have a canonical mapping of the vectors of, because all tangent planes are the same, right? Even if they're not parallel. I mean, they're all planes after all.
Oh, yes, that's true.
But you don't have a canonical mapping,
yes,
right?
yeah.
Is that the difference?
Yeah, this is the difference. Yeah. So what Michael's saying is that as abstract vector spaces in two-dimensional vector spaces, this tangent plane is the same as this one, 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 is the same. They're all the same tangent plane. But that's not exactly true because that's a non-geometric statement. In order to make a vector space look like R2, you have to choose a basis. And you know that choosing the basis involves choosing the parameterization, blah, blah, blah. So if you want to identify tangent planes with each other, you have to be able to do it in a geometric way, which means in a way without choosing a parameterization. And just translating in R3 is something that you can do without choosing a particular orientation or a basis or whatever for the tangent space. You can just go ahead and translate it over. So yes, that's the answer. Yeah. Okay, so now that we have this Gauss map looking like this, the next thing we can do is introduce the associated bilinear form. Okay, lots of language, but the definition is easy. I'm just going to, well, it's up there, I'll redo it over here. Okay, so now we introduce the second fundamental form. So the second fundamental form really is the differential of the Gauss map. It's this dn over there, except I just want to put this thing in a bit more of a, well, let's say this is a better form for it. The derivative of the Gauss map, the derivative of the normal vector, is the second fundamental form. But I just want to put it in this form because this is the way it tends to be done, and it's a bit more systematic. Okay, so the second fundamental form is denoted with an A. Sometimes it's denoted with a 2, sometimes it's denoted with a B, but we're going to denote it with an A. So the second fundamental form is a point P acts on two different vectors, and the output is just the Gauss map, the differential of the Gauss map on V, and then inner product with W. And like I mentioned, we put a minus sign in front. So what does this do? Well, here's my surface, right? And here's my normal vector. And I've got two vectors. I've got V here, and I've got W over there. And both V and W are supposed to be in the tangent space of the surface. So this is okay, so what does this do? Well, the first thing is you take the derivative in the V direction. So you're looking at the way the normal vector changes when you move in a very specified direction, the direction specified by V. So the surface curves, the normal vector changes, and it changes everywhere. But you choose direction V in which to move, and so you're looking at the direction, the rate of change of the normal vector in the V direction. Okay? That's the first thing you do, that's the first part. But that derivative, so V is a vector, V is a vector, D is a matrix, so D times V is another vector. So that derivative itself has several components. So by taking the inner product with W, you're looking at the rate of change of the normal vector in the V direction, but you're looking at the W component of it. There are many components. There's the W component. So what you're really doing here with this definition is you're picking off one of the components of the rate of change of the normal vector from point to point on the surface. If you wanted to be really precise about this, you would take two coordinate vectors, or maybe two orthogonal vectors, E1 and E2. Then you would have the E1 component. You have the E2 component of the derivative of the normal vector in the E1 direction. So it really would be a component. Okay? So this second fundamental form measures the rate of change of the normal vector in the different directions and its different components. Okay. So that's the second fundamental form. We'll interpret it momentarily. But the first thing we should do is prove this important result about the second fundamental form. Namely, it's self-adjoint. Oh, by the way, I should say something before we talk about that. I should say something, some elementary properties here. I didn't put this on here on the slide, but I should just say it anyway. Is it clear that this guy's, 1 second, Ben? Is it clear that this guy is linear? Taking the inner product with W is a linear operation. And of course, dn on V is multiplication by a matrix. So this is really V and W maps to V, W transpose matrix V. So it's linear in both W and V. It's not bilinear. Does that make sense? So elementary property is it's bilinear. Okay, sorry, Trent, you had a question?
I was just wondering what the significance of projecting a second time into a second direction. I could imagine just pulling one component in the direction I wanted instead of then projecting it into W. Does that question make sense?
Sorry, could you say it one more time?
So it sounds like with pulling a component in direction D and then projecting it into direction W, what's the point of projecting it into the direction W?
Well,
no,
that makes sense. So if you didn't project it into the direction W, you basically just have this derivative of the normal vector, dn. And that's actually called your shape. That's called the shape operator. Differential in Gauss map is called the shape operator. So it's a reasonable object too. It's just that if you again project onto a particular direction, you have a bunch of scalar. You have a matrix of scalar. You have a bunch of scalar quantities you can analyze. So, V and W span a two-dimensional, or from a two-dimensional vector space. So really you have four linearly independent components here. The E1, E1, the E2, E1, the E1, E2, and the E2, E2. So you really have four scalars to analyze. And somehow projecting them out allows you to sort of just deal with them separately and ask scalar quantities.
It also avoids having to write down a basis for the tangent space, right? Which is something that we don't like to do.
That's a good point. Yeah, that's right. That's a good point. Yeah, that's true. That's actually, that's in fact a better explanation than I just gave. Okay, so let me say that again. Let me say it again. Yeah. So this is a linear transformation, right? And which means you can only visualize it after you choose a basis. As a matrix, you have to choose a basis first. Because this is somehow a scalar. This is a function which can be okay. Sorry. So there's a thing that is a matrix. If you want to visualize it further, you need a basis. Here's something which you can define all the way down to the actual real numbers that come out at the end. You can define it all the way down to that level without ever having to choose a basis. Yeah. Okay, that's a good explanation. Okay. Right. So the next thing to do, so here's your elementary property, is that this is a bilinear form. It's linear in both V and W. So in other words, or I guess it's a quadratic form, I guess is another way to say it. Right, so it's a quadratic form, and therefore it has four different quantities, four different degrees of freedom. As I said to Trent, you can take 4 different, we can take 2 linearly independent, a choice of 2 vectors here, choice of 2 vectors here. The output is, we get 4 different numbers. But what we're going to prove now is that, in fact, we only need 3 different numbers, because this is going to end up being a self-adjoint linear operator. So what does self-adjoint mean? Let me just remind you. It means that this quantity minus dn at p of vw is equal to minus v dnp at w. So you can switch the order of v and w. It doesn't make a difference. So maybe I'll just drop the minus signs. They're redundant in this case. So this is what we're going to prove. We're going to prove that the order of v and w doesn't matter. Okay? Then we have self-adjoint bilinear operator. Okay, how do we do that? Well, let's choose a basis. Okay, so now that we have defined the thing independently of basis, we're allowed to choose any basis we want to do our calculations in. Okay, so we're going to go ahead and choose a basis, and so the ij component is, so how does this work, right? So we have a function of u into s, and we have e1 equals d phi by du1, and we have e2 equals to d phi by du2. So this is your basis. So this is when I say choose a basis, this is what I mean. Let's parameterize a small neighborhood surface, and let's look at the coordinate, the basis coming from the parameterization. So then the ij component of the second fundamental form is just, I think I forgot the minus sign, but anyway, minus dn by dui and d phi by duj. Right? So it's the derivative of n in the E1 direction, which is the E1 direction, the EI direction is d by dui, right? So you differentiate in the I direction. And then we take it against EJ. So this is EJ. And this here is dn in the EI direction. Okay, so now a little bit of magic happens, but it's the same magic tricks we've used over and over again. So I'll write it down, and then you can tell me why it's true. Why is this true? Yep,
This looks like the Flaw rule.
That's because it is the product rule. Exactly right. So I have an inner product of two things. What's the derivative of a product? Well, it's the derivative of the first times the second plus the derivative of the second times the first. So let me move, okay, so let's say that's true. Let's take this and move it in here. I get dn du, comma d phi du, plus n d squared phi du squared. I get two terms when I move this in here. And because of this minus sign and because of this plus, that second term cancels, and all I'm left with is that back there. Okay, so magic trick number one is to use the product rule. Magic trick number two is the chain rule, but that actually doesn't come into play here. Magic trick number three, what's the value of this? n is points in what direction? Normal to the surface. This points in what direction? Tangent to the surface. So their inner product is going to be 0 no matter what choice of u, and so if you differentiate, this goes away. So magic trick number 2 is to recognize something as orthogonal and set it equal to 0. Okay, so this now is equal to plus the inner product of n with d squared phi by dui duj. Okay, so magic trick number 4 shows up. This one we've never used before. This is the famous equality of mixed partial derivatives. So at this stage, since the partial derivatives are on the phi, and phi is 3 real valued functions, I can swap the order of the derivatives. Instead of it being ui uj, I get uj ui. And now that I've done this, does it make sense? Right? So now that I've done this, I can undo these steps. I can go in reverse. So this equals, change colors, I can emphasize this. This equals same steps in reverse. This equals to minus inner product of dn duj with d phi dui. So I now have succeeded in swapping these two guys, right? So that means I get self-adjointness. Right, so this is equal to a second fundamental form at ji. So aij equals to aji. So we have a self-adjoint operator. Okay. All right. So this is the important calculation that we always do when we first introduce the second fundamental form, to show that you have this self-adjointness property. Okay. Next, we're going to talk about various interpretations of the second fundamental form. Okay, so there are let's say there's 3 different things to say. I think I'll be able to say everything on this slide in detail, and then I'll have 2 more things which I'll just explain without going into calculations, and I'll post the calculations as supplements on the webpage. Okay, so the first thing to say is that the second fundamental form measures curvature of the surface. Okay. How does it work? Well, let's say I want to again consider curves lying in my surface. So what I'm going to do is show this formula here. I'm going to say that if we have a curve which is restricted to the surface, a curve lies on the surface, then its Gaussian curvature, the standard Gauss curvature vector that we talked about on the first day, the second lecture, its Gauss curvature, the normal part of it, measures something about the surface. The normal part of the curvature is related to the second fundamental form. It doesn't relate to the curve, it relates to the surface. Okay, so let's draw some pictures. What I'm going to have is my surface, as usual, and I'm going to have a curve that lies in the surface. So this is C of t. C goes from I into R3. C of I lives inside the surface. Lose my surface. And let's take a point here. Let's make this P, which is C of 0. let's say the curve just happens to start to be 0 there. And let's give this point a direction vector. X lives inside the tangent space of the surface. X is equal to c dot. So this is c dot at 0 equals to x. Okay. So right. So this is our setup. Now now c double dot, the acceleration vector of the curve. Okay, I guess let's go ahead and say just let's just say it's parameterized by arc length of the curve, just so we can talk about the second derivative. It means it's perpendicular to the surface, to the curve. So the second derivative points like this, right? This is c double dot at 0. So this vector here is not necessarily perpendicular to S or nor parallel to S. It's just a it's just a vector which sticks out of the space somehow. Okay? Because this c double dot is computed from the curve itself. It doesn't really know much about the surface. The curve exists on its own right in space, after all. Okay, but as soon as I do what this left-hand side tells me to do, as soon as I do that, now suddenly I make the curve aware of the surface. Right? I'm taking the inner product with the normal vector of the surface. So let's keep a normal vector to the surface here. Normal vector to the surface, and this is my point P. Okay, so since I've got a two-dimensional blackboard and since I'm drawing stuff, it's not necessary. Maybe you can't really tell what direction c double dot is pointing in. But let's just say it's not parallel to the surface, it's not perpendicular to the surface, just sticking off into space somehow. So the normal vector might be like this, right? And the tangent plane might be like this, and then the c double dot is like this. We don't know, okay? But let me take the curvature vector of c at 0 and inner product with the normal. But of course, since we're in the arc length parameterization, I can say this is c double dot at 0 with the normal vector. Okay, so far so good, right? Okay, so I want to relate this to the second fundamental form. How do I do that? Well, let me do this. Let me do it like this. What do you think? What am I going to do next? What direction does this vector point? I told you we didn't know much about c double dot, but we do know something about c dot. What direction does that vector point in?
Tangent to the curve.
That's tangent. This guy's normal. So I'm in a similar sort of setup as I am over there, right? As I was over there, right? What I'm going to do next is I'm going to pull the second derivative out. And I'm going to move it over to the other side. And I guess I should really put it like this now, right? Because now I'm looking at the derivatives of the normal vector as you move it along the curve. Okay, so what I'm saying here is that this is the derivative of n along the curve C. So in other words, it's, let me do this bigger. This is d by dt of n at the point ct. So the point's moving along the curve. So yeah, I'm doing the same trick as over there, which is I pull this derivative out, and which allows me to move it over to the other side. And as long as I use the product rule correctly, this is a correct statement. But again, that's perpendicular to that. So this cancels. So what I get, I'm going to take it all the way to the other blackboard over there. Okay, so what I get is I got my curvature vector at C at 0 times the normal is equal to minus inner product of dc by dt with dn at C of t by dt. This is exactly like this. This is minus x, because C dot was x, as I said over there. Well, never mind x. Let me just put C dot down. C dot at 0, and this is the derivative of the Gauss map acting on C dot. Or in other words, it's precisely what's written there. It's second fundamental form on C dot. Okay. Right. So, what are we saying? We're saying that the good old-fashioned lecture 2, by good old-fashioned I mean all the way back to lecture 2 of the course, the good old-fashioned curvature vector of the curve relates to the second fundamental form in this way. Let me give you a nice pictorial interpretation of that.
So you could have avoided a lot of these steps by just using the self-adjoint property?
Probably, yes. Where? So where?
C double dot MP, self-adjoint is C dot EN.
Yeah. Yeah, okay. Yep.
I want to make sure I was composing this right.
Yep. You're right. Okay. The picture. Here's a nice picture. This is a good picture. So here we have our surface, let's say. So make it bend a little bit from this. Okay. So what you do is you go to a point here, and you draw a curve in the surface. And what you can then do is you can sort of straighten the curve out so that you can cut the surface with a plane, which is perpendicular to the surface. Right? Okay, sorry, this is a bad. Yeah. Okay, what I want to say is that you can take a circle. You can take a circle with same curvature and touch up to the curve. In fact, same curvature and also same C double dot. So I have the surface here, right? And I draw a curve on the surface. I know that this curve is going to give me the second fundamental form. And what I then do is I take a circle that has the same curvature and the same orientation, the same C double dot, and I move it until it touches the surface. So what I'm doing is I'm making this second order contact between the circle and the surface. And because the curvature of the circle is the same and the direction is the same, I'm picking up. I'm picking up the same right-hand side, but now I can interpret the left-hand side really nicely. Because the left-hand side, what's the curvature? What's the curvature of a circle? It's 1 over the radius, right? So what I'm getting, what this second fundamental form is saying is I'm picking up this second order I'm picking up the curvature, or 1 over the radius, of the second order circle that touches the surface at that point. So I'm getting a radius of curvature. I'm getting a radius of curvature at the point P. I'm getting a radius of curvature at the center point.
5 minutes.
Oh yeah, thanks. So I'm just gathering my thoughts here. Okay, right. So what the second fundamental form is saying is it's giving you a radius of curvature in a particular direction. You choose the direction, then what the second fundamental form gives you is 1 over a radius of curvature in that direction. And because you're allowed to vary this, you know, you can move this, you can move your C double dot, your vector around, and you pick up different radii of curvature. It's a two-dimensional surface with different curvatures in the different directions. Okay? This is what this calculation actually is giving us. It's giving us these different radii of curvature. So now my bullet point here says that let's go ahead and let's vary this vector as you go all the way around. Then this quantity, because it's giving you numbers on the unit for different directions, it has a minimum and a maximum, right? Minimum and maximum. Let's call you have the minimum curvature and the maximum curvature. Those are going to be called the principal curvatures of the surface. So the largest and smallest, as you vary around, are the principal curvatures. And the directions that you've gotten when you get minimum and maximum are called the principal directions at the point. Okay? Now, I say here that there are eigenvalues and eigenvectors. So this comes from, we won't go into this, I'll just say why it's true. This comes from linear algebra. When you have a quadratic form, like the second fundamental form, you have a quadratic form, and you vary it in this way, you pick up this, you can prove that you pick up the eigenvalues and eigenvectors of the surface. So this statement comes from linear algebra. It's just general fact about quadratic, about the quadratic form. And because the quadratic form is self-joint, as we just proved, what we know about those principal directions is they are orthogonal to each other. That's not necessarily, that wouldn't be the case if the quadratic form weren't self-joint. But because it's self-joint, you have these orthogonal principal directions. Okay, and now we have these guys. The next two curvature quantities are the mean curvature and the Gauss curvature. The mean curvature is simply the average, well, not the average exactly because I've taken up the factor of 2, but anyway, the sum of the principal curvatures. And the Gauss curvature is the product of the principal curvatures. So these are good numbers because remember that you don't have to diagonalize the second fundamental form to get those numbers. To get K min and K max, you have to do an eigenvalue computation. You diagonalize, right? But to get these, so to get any other combination of K min and K max, you might think you would just need to use, diagonalize first, which is a lot of work, and then make your combination of K min and K max. But in the case of these particular numbers, that's not true. Those are special numbers. Remember that the trace of a matrix is invariant under choice of basis, and so is the determinant of the matrix. So what that really means is you don't have to diagonalize the second fundamental form to get your hands on mean curvature. You just take its trace. And I'm going to explain this a bit better in supplementary material. You have to take the trace in the right way, but never mind. And similarly, to get the product of those two things, you have to take the determinant of this linear transformation. So product of eigenvalues is an invariant quantity. It's equal to the determinant. So is the mean curvature. So you don't need to diagonalize to get your hands on these two numbers, trace and determinant. But for more, you do have to diagonalize. Okay, so right. So let me take 1 or 2 more minutes, and then I'll stop. Okay. No, in fact, let me just stop here. We'll continue this. There's a bit more to say. I don't want to rush through it. So I'm going to continue this lecture a few minutes on next month. But I think you probably have enough to do your homework at this point. I'll just double check, but I think you do. Okay, so that's it for today. Thank you very much.
And your homework is posted on the course website, homework 2. And Adrian's going to post a supplement, I guess. And please take a look before Wednesday, because we kind of need that material for Wednesday's lecture. Cool. Thanks, guys.
And I have a graded